Right. Precalc outline point 7. We're going to talk about probability with permutations and combinations. What I realized, though, is that the book doesn't actually go into what is probability of something. They talk about experiments, they talk about sample space there, and then they kind of get right into this whole idea of finding how to figure out when you start putting combinations and permutations together, the probability. But what is probability in general? So first of all, let's talk about an experiment. An experiment is something, a situation that has a chance or a probability. So it's a situation with a chance or probability. So maybe we should talk about probability at that point. So if I asked you, what's the probability of landing a heads on a coin? 50-50 or 1/2? 1 to 2, yeah? If I have a die and I throw a die, what are the chances I get a 5? 1 out of 6, because there are 6 sides, so there's 6 outcomes, but there's only one, the 5, that I want. Yeah? Yeah. So probability is the number of wanted outcomes divided by the possible outcomes or total outcomes. Remember, that's what probability was. What do you think the sample space is? All possible outcomes. A sample space is all possible outcomes. So when I talk about a coin, heads and tail is the sample space. A die will be 1, 2, 3, 4, 5, 6. Okay? So now we're going to go into a concept of some of this, guys. This one is definitely should be ringing a bell from last year in geotrig. Because the fundamental counting principle, without having to be so wordy, that if A things happen A ways, and B things happen B ways, if I were to stack one after another, then A things followed by B things, the total number of outcomes would be A times B. That kind of make sense? If I have a coin and I flip it, I have 2 outcomes possible. If I take a die and I throw it, there are 6 outcomes. So if I do one after another, it's 2 times 6, which is 12 total outcomes. What are those outcomes? It's a heads and a 1. It's a heads or a tails and a 1. It's a heads and a 2. A tails and a 2. There are 12 of those combinations or outcomes, right? You guys kind of follow that? Your dress code is more than 2 things. It's outerwear, a top, and a bottom. We'll say those 3 things. Each one of those is an independent event. We're going to get to that. That if you choose to have a sweater on or fleece or a different type of outerwear, you can have a red, white, blue, Oxford, all these different things, shirts. Those are other outcomes. You take all of those and multiply them together. That's how many different outcomes or outfits you can have. So if you have 17 different events happening one after another, you just multiply the number of choices all together. That's the fundamental counting principle. You guys have used that before. And again, like I said, there are independent events and dependent events. Independent means they don't depend on each other. They're completely separate. When I roll a die and then flip a coin, does it matter what I rolled the first time? Will it affect what I get on a heads or tails? No. I could roll a die, pick it back up. Did that last roll depend on what I'm going to roll now? Or vice versa? No. They're independent of each other. Then you have dependent events. Now, what if I had a hat full of colored marbles? And I took the marble out. Is that next grab going to be different than the first grab? Yes. Because in that case, there's one less marble. There's one less of something, right? Those would be dependent events. Any questions? So the first question we're going to come across here is if there's a restaurant. So your favorite restaurant has a dinner special. And part of that dinner special, they can select from one of 6 appetizers. You get a soup or a salad. You get one of 12 entrees, and you get one of 8 desserts. How many different dinner specials are there possible? Right. So you have how many choices the first time? Oh, you got 6 appetizers times soup or salad, so there's only 2 choices, times 12 times 8. How many dinner specials are they actually providing? Take your calculator, guys, out. 6 times 2 is 12. 12 times 12 is 144. What's 144 times 8? 1,000? 152. There are 1,152 outcomes. Dinners. Possibilities. That's a lot. That means you could go there for about, what, 3 years? And never have the same dinner. Or eat there for a whole entire year, every single meal, and you could have every single one. It would take probably about a year or more. Right? There are 3 meals a day. If I divided that by 3, how many days would it eat? But what if they gave it to you all day? Okay? So that's the power of this. So, wait a minute. Hey, Garrett works for a bookstore. Because you didn't know that, did you? And he is arranging the best 5 sellers on a shelf display. Ooh, this comes right out of that Geo-Trig book. If he can place the books in any order, how many different ways can Garrett arrange the books? It's 120. Interesting, because we have these 5 spots on our shelf. 1, 2, 3, 4, 5. And I'm going to place a book down. Does it matter where I place the book? So, just to make things easier for us, we're going to stack that book at the far left. And I have 5 of them. Would you agree? The next time I do this, how many do I have? And then 3, 2, 1. So 5 times 4 times 3 times 2 times 1 is 120 ways to stack those books. Why? Because this is the thing. I can take that first book, and I could have put it there. I had my 5 books. I could choose all 5. I could put it there. My next one, maybe over here. So I have 4 to choose from. And then, well, maybe over here. And then here and here. But is it those numbers multiplied together the same as 120? So it doesn't matter. Back in Geo-Trig, they would have said there was red books and blue books. And then you would have to multiply by 2 because you could put the blue books first or the red books first, right? Great stuff. But you guys remember a better way of multiplying that? 5 times 4 times 3 times 2 times 1? Factorial. So a factorial, guys, is that n factorial. It's a way for us to multiply descending order of numbers. And so it equals n times n minus 1 times n minus 2 times ... times 1. So, in this case, we could use 5 factorial. And 5 factorial means 5 times 4 times 3 times 2 times 1. If you're using a standard scientific calculator today, you will find it underneath your 3 button. To do that, you'd have to hit 5, second 3. if you are using a graphing calculator, you probably more likely have to hit math. There's a math button. If you hit math, actually you put 5 in first, a lot of times, still have to hit 5. Go to math, go to the right 4 times, I think it is, till your category becomes PRB. And I think it's the 4th one down. Okay? That same place, remember where that is, because you're going to use the 2 above it as well. So, you can hit 5 factorial, and it should give you 120.
Ow.
Go to math.
Do I have to hit second?
It's the
No.
4th, the little...
Hit math by itself,
It's this
page
one.
over to PRB. Yep. That's the one, number 4. Okay, so now we should know how to do that. So these things, guys, what this is going to come down to is we're going to have permutations. Permutation is an arrangement where order matters. It's an arrangement where order matters. In the next slide, I'm going to show you some formulas on how we can use shortcuts on our calculator and do it the long way. So this is an arrangement that orders matter. It matters when you use your books and the order has to go in place. So what are those formulas? They're right there. The one on the left is just kind of just a play on the right, as in if I'm looking at a problem,
Can you make them bigger, please?
a little bit. So the one on the left is just saying that it's NPN, permutation. What it says is the number of permutations of n objects taken n at a time. Basically, if I have 5 things and I'm going to use all 5 of them, then it's just n factorial. The whole 5 books, n factorial, 5 factorial is there. But a lot of times when we talk about permutations, I am thinking of only using some of them. So there are 26 or 27 of us in this room. So if I said, hey, we're going to form a group of 5, how many different permutations are there? Well then, it's 26 P5. 26 people taking 5 at a time. How many different groups can I have? Or permutations, orders can I have? So that'd be 19, or not 19, sorry, that was last hour. 26 P5. You guys can find it on your calculator. If you put this on your calculator, it's in the same PRB section. If you're using a scientific or graphing calculator, you may have to put 26 first, hit PRB, and then hit 5, for NPR, sorry, NPR, and then hit 5, enter. It's a pretty big number, isn't it? What do we got? Just rattle off the numbers. 0, 0, 0. There's 78 million, almost 79 million permutations from this. 720, something like that. Of this, taking 5 people from this class and standing them at the front of the room. Well, maybe wait, is there less zeros? Uh-oh, guys. There's only 2 zeros. That makes it a little bit lower. Okay. So almost 8 million. Even though that's still pretty big, yeah? So you're saying, guys, listen up, that if I stood people and I said, okay, You 5 people, go stand up at the front of the board. That's only one.
Actually go do it.
No. That's only one permutation out of almost 8 million. So guess what, guys? I have this magical set of group of people that I'm going to say is part of my permutation that'll go up to that board. What's the chances, what's the probability that you guys can get that combination? Or that, sorry, permutation. 1 in 7.8 million. Think of the Powerball. I think there's 6 numbers total, 5 and 1, right? I don't know what those numbers go up to, like 60, I think, or more, maybe even higher. So say it was just 60, all 6 numbers. That's 60 times 60 times 60 times 60 times 60 times 60. Only one ticket has that sequence of permutation. Someone almost won a whole full $1 billion the other day. Okay?
Well, I mean, think about how much goes tax. 60% goes
Well,
tax.
it does. It's still, they won a lot of money. Okay, but
They didn't make $1 billion.
okay. Here's the thing, guys. This is what you need to recognize. So let's just say this row right here, this column, went to the board, and I said that was the magical number up here. Here's the thing. Guys, listen. Tessa was first. Kiki was second. That is what a permutation would be. But here's the thing. If we send Tess to the back of the line, that's another one. And keep doing that, right, until all of a sudden it repeats. Okay, that doesn't count. But then all of a sudden, what if I put the order just flip-flops in people? You're like, wait. That's the same group of 5 people, right? Yes. But they're different permutations of 5 people. Kind of seeing that? To us, we wouldn't recognize much of a difference. It's the same 5 people, whoop-de-doo. But because that order does matter, whoever's in seat number 1 sets up a permutation of its own. And then they can move, someone else can move in. Or the people behind them can move. Okay? So be very careful on that. So, an alarm system requires a 7-digit code that uses 0 through 9. Each digit may be only used once. That's kind of nice. How many different codes are possible? Let's use permutation notation. Because the order does matter. I got to put a code in, then I can put another code in, put another number in, right? So, I'm using 7 digits out of how many? 9. No.
10.
10, because 0 is in one of them. So 1 through 9 and 0. So what do I have? I have 10. P, how many am I using? 7. Put it on my calculator. How many permutations, possibilities are there? It's a fairly large number. Where to begin? There are 604,800 different codes that use 7 digits out of 10. The 10 digits. Only using 7 of them. Using all the number only once. Think if you added those numbers back in. It gets even bigger yet. That's what makes it hard to crack a code that's 7 digits. Which is bigger than it would be if there was only 4 digits. Which most of us have on our devices. Now, on the very bottom there, it says, what if this code is randomly generated? What is the probability? Which means now you have the option of coming up with a code. How many codes are there when the first 3 digits have to be odd? Whoa, man, this totally brings back last year, and you guys are trying to avoid or forget that. Now, let's think of this. There's this really long code, 7 digits, and somewhere there's a break in there. There is some that have to be odd, and then the rest of the code can be anything it wants to be, right? Let's think of this. How many of them have to be odd? 3 of them, so I have to choose 3 of them. How many of them then are not odd or whatever they want to be? There are 4 of them. It has to make up 7. Here's the cool thing. I can take permutation notation from part of the code and multiply it to a permutation of the other part that can be separate, and multiply them together, and I have the same value that will result if I put them all in order. As in doing that 5 times 4 times 3 times 2 times 1 thing. Because each section talks about like almost being like an independent event. The fundamental counting principle says I take the number of outcomes and multiply it to the other one. So, how many choices are there in the odd group? How many choices are in the odd group? How many odd numbers are there?
3.
There's more than 3 odd numbers
Wait, in the 604.
in your 10-digit options. There are 5 of them that are odd. How many am I using?
3.
Only using 3. Well, this is where it gets tricky. That second group, how many do I get to choose from?
4.
7. Why 7? Because the initial rule said I can only use a number once. And I just used 3 of them up for my first 3 digits. How many of those 7 am I going to use for that code, though? 4 of them. It happens to be, what is the 5p3? 60. What is 7p4? 840, which would result in how many of the codes have odd digits first?
5 or 50,000.
Now, I didn't read the question very well with the other classes, but it says, what is the probability that the first odd, if a code was randomly generated, would have the first 3 odd? Well, guess what? You have this many to choose from now, right here. You have 50,400 to choose from out of, these are your wanted, out of 604,000. So the probability would be taking the 5,400 divided by the 604, 800. That would be the probability of you just randomly choosing or picking a code and it being under those guidelines. Questions? Combinations are the same thing. It's an arrangement, but this arrangement does depend on, doesn't consider order. And so the combination uses the same kind of setup, but this time NCT, or CR, sorry, it's R. That's an R. And it's still n factorial over n minus r factorial, but then they put the extra little r factorial on there. Because you're dividing out the repeats. Guys, go back to our team. My team goes to the board. They shuffle themselves up on that team. Is it still the same team? Yeah. Combinations don't care. If I'm going to create a team of basketball players or wherever, a team's a team. It has the same players, it's the same thing. So therefore, it says the main difference between a permutation and combination is whether order is considered. Permutations, yes. Combinations, no. Take a look at E, F, G, and H. Taking 2 at a time. Permutations, there's a whole lot more permutations than there are combinations. Why? Because E, F, and F, E is the same group. It doesn't matter which way I put them. I switch them around, do, si, do. It's the same couple. Why do I want to restate that? I don't. So sometimes order doesn't matter, and combinations is the way to go. Okay? If you look at something or a group and you can't tell the difference between them switching around, hey, is there any different team? No. That's a combination. So we get rid of those. We get rid of the doubles, right? The extras. In that case where we had those 5 people, you had to get rid of a lot more combinations or permutations because there's a lot more switching that can happen on that particular group. Can I turn?
Yes.
Anyone else? Yeah? Okay. So really I just want to talk about that first question, that if there are 7 seniors, 5 juniors, and 4 sophomores on the PEP squad, Mr. Reinhardt needs to choose 12 of those students out of the group to sell spirit buttons during lunch. Because you got to have spirit buttons to be PEP. How many ways can 12 of those students be chosen? So that group of 12, doesn't matter who is in that order, right? Doesn't matter who's chose first or anything like that, because the group will not change in its appearance of who's in it. So this is a combination problem. How many people does he get to choose from, though? 16. If you add up 7 plus 5 plus 4, there's 16 people. Combination, taking how many of them? 12, and I put that on my calculator. How many different combinations are there? Still, I think there's quite a bit. Still over 1,020 different combinations. That means there's 1,820 different groups that can be made. Just like if we did that whole idea with our groups, do that with our class. We got a little bit of time. What if I did that 26 combination 5? Now we're the extra adults, right? Where my row just kind of switches their order. How many of these things do we have? 26 combination 5 at a time. 65,000. So just about 66,000. On our problem before, we said there were going to be almost 8 million. We eliminated a lot of groups because all they did was shuffle their feet to one spot to a next, right? That's a huge factor of a difference. Of the magnitude of what, 100 times smaller? That's crazy. Okay? Any questions on that? So a lot of it comes down to recognizing, is it a permutation, is it a combination? Is order important or is it not important? And then take those outcomes and multiply them all together. 1 through 31 every 3, page 33.7. Make sure you put your name on your assignment. Make sure you put the assignment name, point 7, page number, and the assignment. Have a great day.